This is the chapter 27 homework. So these are the conceptual questions. They're due today, and it's not the 4th. Why am I doing that? It's the 9th. I'll put that down. I'm going to move that up here. Going to make it bigger. Yeah, we're going to make that for the 9th. Ha. Oh well. At any rate, so what we've got here is we've got a cube, and it showed positives all over the place. But the idea is, if you look at those positives in the cube, it's not a sphere, it's not a cylinder, and even if the cube has uniform density of charge, because of the way the corners act, it does not have a type of field symmetry. So the field would not be spherical or would not be pointing out like it would in a cylinder, so we cannot determine the field symmetry. So you can't rotate it translationally or rotationally. For question 2 here, we've got our field lines pointing into this triangle and then out. Because the same number are going in and they're all 10 newtons per coulomb as they're going out, there's no net flux and there's no charge enclosed. Here we have 3 arrows pointing out from the area, so therefore there's got to be a positive charge enclosed since the net flux comes out, and here there's got to be a negative charge enclosed. Going down, that was bad. Going down to these ones, these are the shapes that are circled. Each of them had a positive Q or negative Q, so this is +3 and -2. So the flux is the net charge enclosed over vacuum permittivity, so this is plus Q over vacuum permittivity, which is epsilon naught. This is negative Q. This is 0 because nothing's enclosed. So if I had a different type of shape, and let's say here I have this as nothing, and here I actually have this as this. If I make this shape, this is annoying. Something like this. Obviously, it's flux then. It had +3 charges and -2 would be plus Q. This would be minus Q. +3Q, -2Q, stuff like that. So all depends on what's enclosed. Here, this is a really nice one. So A is +4Q over epsilon sub 0. B, -4Q over epsilon sub 0. C is 0, because no net charge. E, also 0, because no net charge. D, +3. For number 7, this is actually pretty interesting. So this is a balloon that says it has a uniform charge on it, and basically the balloon is blown up. And so if we pick an imaginary points in space, 1, 2, and 3, it's asking how the flux changes, if at all. Well, if charge is uniform on the balloon, and if it was a conductor or a mylar balloon, the charge would spread out no matter what, in a uniform manner. But if it's like a latex balloon, it might not do that. Either way, doesn't particularly matter, because it said that it was uniformly charged. So 1 is inside the initial balloon and inside when it's blown up. So by definition, no field strength. So it does not change. Here, point 2 is initially outside the balloon, so it would experience an electric field. If the field's positive, it'd be pointing outward or in a positive way. Here, once the balloon's blown up, 2 is inside that space, so there's no flux. So E2 would decrease in strength or decrease in magnitude of strength. E3 would stay the same, and it would be non-zero. And you might think, well, wait a minute, this surface is getting a lot closer to this spot in space. If there's positive charges all around the outside here, wouldn't the flux get stronger? Well, this edge is closer to 0.3, but many of these spots along the outside of the balloon are getting further away. So the idea is that the charge still acts all as if it is coming from the center. and that position hasn't changed. So flux for E3 stays the same also, but it's non-zero, unlike 1, where the flux would stay the same but be at 0. Q8, student 1 is correct. The field depends on flux and surface area, but flux itself only depends on the enclosed charges. So field strength depends on those. And it goes back to the total formula for Gauss's law, just something like this. Let's do nice purple thing here. And basically what we've got is electric field is equal to, flux. And I can't do the symbols on this. Electric field times area equals charge enclosed divided by epsilon sub 0. That's a crappy way to show that. So that's it.